Welcome to today's Westpac webinar, The Shocking Truth About Engineering More Sustainable Packaging. My name is Roy Strunin. I will be your moderator for today's webinar. A few housekeeping items before we start. All attendees are muted and will remain muted for the duration of the webinar. Next, let's take a moment to ensure that everyone is ready and familiar with the webinar control panel. You have a control panel on the right side of your screen. You can minimize the panel by clicking on the orange arrow button in the upper left corner. You may expand the panel by clicking on the same button. You can submit questions at any point through the chat button located near the bottom of the control panel. We'll be answering questions during the presentation. If we are unable to address all the questions, we'll follow up by email afterwards. For those of you registered and logged into the webinar, you can download a copy of the slide deck now. Look for it on the webinar control panel. Okay, let's get started. We are very fortunate to have a very qualified presenter today. Greg Schwinghammer is a principal engineer at Westpac, a certified employee-owned company. With over 20 years of experience at Westpac, Greg has held roles ranging from test engineer to general manager. His primary focus is ensuring customers receive the highest quality service and timely results for all testing projects. Recognized as a go-to expert in the field, Greg provides trusted guidance on test protocols, equipment capabilities, and package design optimization. He is an active member of ASTM committees D10 for packaging, F02 for primary barrier packaging, and E60 sustainability. He holds a packaging dynamics professional certification from ISTA. I'm going to hand the microphone over to Greg, who will begin the presentation now.
Great, thanks, Roy. Let me tell everybody a little about Westpac. We were founded in 1986. That means we've been around for 39 plus years. We'll celebrate our 40th year coming up here in the next 6 months. We do over 3,000 tests a year across our 3 locations, one in San Jose, California, one in Union City, California, and one in San Diego, California. All 3 sites are ISTA certified and ISO 17025 accredited to do the testing that we can do. Now let's jump in to talk about kind of damage boundary testing and how it can help you. So has this happened to you? Has your boss either come by your desk or sent you a message saying, hey, we just got our new corporate sustainability goals. We need to reduce our packaging by 20%. And, I'd like you to lead the corporate initiative to meet those new goals. And you're sitting there at your desk going, oh no, what do I do? How can we eliminate packaging? How can we make sure that our product still gets to our customer on time and meets all the requirements of protecting our product? You can use damage boundary testing to do that. So today we're going to look at how damage boundary testing can help you meet those goals and you can maybe even exceed them. We're going to first talk about why you would look at using damage boundary testing, and then understanding what damage boundary testing is and how it works, what a cushion is and how it works, and then interpreting the damage boundaries results, comparing it to your package test results, and how you can use that to figure out how much margin you have in your existing packaging. So first, what is damage boundary theory? Damage boundary theory is a method of determining the ruggedness of your product, or in other words, the fragility of your product from shock. What damage boundary testing usually is used for is typically used for equipment that needs engineered cushion systems, so like computer products or TVs or those type of things. But it can be beneficial for analysis of any type of product. We at Westpac, we've done damage boundary testing on auto injector pens, food products, consumer goods. So really anything that may get impacted or dropped in the distribution environment can benefit from damage boundary testing. Why would you want to use damage boundary testing? When you know the ruggedness of your product, you can determine how much packaging is needed, and if packaging is needed at all, or in the case we're talking about today, how much margin you have in your existing packaging can you eliminate to help meet your sustainability goals for your company. So let's talk about why you would need a package. So What you see here is a qualitative representation of how severe the distribution environment is. This is different for less than truckload, e-commerce, CPG, cold chain. But at the end of the day, imagine that this bar represents all the drops, vibration, compression, altitude, temperature, humidity, solar hazards that your product and package or your product will see in the distribution environment. So now let's look at this next bar. Let's say your product is pretty robust and can handle half of these inputs independently. That means you don't need to have a package to survive the distribution environment for half of the packages. So what happens? What do you use the package for? The package protects the product for that additional environment ruggedness that it needs protection from. So looking at that, what if you don't have enough packaging? So if you don't have enough packaging, you can have damage in the distribution environment and your customers receive damaged product. Really what we're going to focus on today is this next one, is what if you have too much packaging? How much margin do you have, or how much waste do you have in packaging that you can now reduce and meet your packaging requirements? Another thing to look at is if you're in that third column over and your package is ideally engineered to protect your product, what can you do to reduce packaging? You can go to the product team and say, hey, our package is ideally engineered to protect it. Here's my data that shows that. And you can help make data-driven decisions and increase the robustness of the bare product so you can then reduce the packaging. And you get savings there. So now let's look at damage boundary testing and how it works. So damage boundary testing is a standard that uses critical velocity change and critical acceleration to figure out how fragile your product is. Basically, that green bar we looked at on the previous slide, and it determines, okay, what is damage and what is not damage. So looking at that, the first one is critical velocity change. Critical velocity change is a half sign test. This is to determine if you need a package at all. So you keep increasing the velocity change, which is the area under this curve here, to determine how much energy it takes to break your product, and it's measured in inches per second. So yeah, this is a half sine waveform. Make sure I got all my points here. So to do this, you would keep, like I said, keep increasing the energy until you have failure. I'll walk through it in a slide here once we talk about the other side of the damage boundary test. Once you know the critical velocity change, you will use that velocity change in a square wave pulse for the critical acceleration. Here's a video of a quick critical acceleration shock test. So it takes that velocity change and you keep increasing the G levels, holding the velocity change constant to get your critical acceleration. And once you have both of those, you will get your damage boundary curve. So kind of let's walk through that. So we have here our critical acceleration or critical velocity change. We do one shock, it passes. We increase the velocity change, it passes there. We do a third one, it passes. We do our fourth critical velocity change and the product fails. So that is now our critical velocity change, or V sub C. And let's say for this case, it's 80 inches per second. We then take that 80 inches per second, multiply it times 1.57, and that is now our critical velocity change that we're going to use for our critical acceleration. So then we start doing our critical acceleration on the trapezoidal waveform, and it passes a second time, it passes a third time, passes a fourth time, or it fails the fourth time. And now we know our critical acceleration is approximately 70 Gs. So we know that anything above 70 Gs and 80 inches per second, our product will be damaged. So now we know that we can now go engineer a cushion system to make sure that our product sees less than 80 Gs and less than 70 Gs and less than 80 inches per second. And for this test, you would want to do this for each orientation of the product for each leg. So you need a total of 12 units to complete this test correctly per the standard.
Greg, we have a question. What if I don't have 12 products to do damage boundary testing on?
That is a great question. So if you don't have 12 products, you can do a couple of things. You can use equivalent velocity change. You can calculate what your equivalent velocity change for a drop height you expect your product to see, and just do the critical acceleration based on 1.57 times that velocity change, or you can determine which is the most critical orientation of your product or the most fragile orientation of your product and do damage boundary testing just in that orientation. So you can get from 12 units to 6 units down to 1 unit. The thing is, it's a much riskier scenario to do that. That all said, in my career at Westpac over the 24 years, I have only completed 2 full damage boundary tests. And that's all I've seen in the company we've ever done full damage boundary. Usually people will make the choice of reducing to either 6 units or 1 unit. But, you know, reach out to Westpac and we can walk through what best suits each person in that question or in that scenario. So now let's talk about cushioning and how it works. So if you're a packaging engineer, you've been doing packaging for years, this may be old hat to you, but if you're not a packaging engineer and you've been assigned how to reduce the amount of cushioning, you need to know how a cushion works first. So when you drop something, it's going to accelerate at 386.4 inches per second until it hits the ground. And then there's going to be a certain amount of energy that goes into that product over a certain amount of time. And that's the velocity change, the area under this curve, which is the velocity change. And then the way a cushion works is it takes that velocity change and spreads it out over a longer period of time. Because when we're dealing with packaging, we're never going to get to critical or maximum velocity or critical velocity where it's going to, or maximum acceleration where it can't go any faster. It's going to continue to accelerate until it hits the ground. So that energy is going into that product no matter what. So what the cushion does is it takes it and spreads that energy out over a longer period of time, which brings the G level down. So the area under the blue curve here is the same as the area under the red curve. Pretty interesting stuff, huh? So how do we take that theory and apply it to engineering a cushion system for our product? So we use what's called a cushion curve. And a cushion curve shows a particular packaging material of a given thickness and how it behaves at different static loadings for different drop heights. So you see here, we have a cushion curve for a 12-inch drop, an 18-inch drop, a 24-inch drop, a 30-inch drop, and a 36-inch drop. And you can see here, it's for the 2nd through the 5th impact. So the way a cushion curve is developed, you do your initial drop on a piece of cushion, and then you average drops 2 through 5. And so now let's look how to read a cushion curve. So a cushion curve in the x-axis has static loading or pounds per square inch. And the y-axis has G's. This curve is for 1.2 pound per cubic foot polyethylene foam cushion for a drop height of 30 inches. So, and for 1, 2, and 4-inch thick material. And this similar cushion curve will come back later in the presentation. So as you can see, the cushion curves are for very specific sets of scenarios. And so how to read the cushion curve? First, you find the curve that best fits your deceleration level. So if you remember, our product had a G level of 70 Gs that it saw during damage boundary. That's the G level that our product failed at. So we want a cushion curve that will be able to protect our product or have it see less than 70 Gs when dropped from 30 inches. So looking at this one, you want to load the cushion curve, or you want to use the cushion curve in the belly of the curve. So really you want to be in this bottom area between these two blue lines. So really for 70 Gs, we couldn't use 1-inch thick material. So we're looking at 2 and 4-inch thick material. And the belly of the curve here is at the really, at the 0.9 PSI loading. So if you have let's say your product weighs 20 pounds, you would take your 20-pound product and divide it by 0.9, which means you need 22 square inches of cushioning material for this very specific cushion. And again, this is the part of the engineering of the cushion system that helps you figure out how much cushion you're going to need and where to load it and all of that. So now let's take that 22 square inches of cushion and see how it's distributed. So we chose the 2-inch thick material because that was the lowest. Oh, and if we look here, 70 Gs is right here. So the 2-inch thick material loaded at 0.9 PSI is perfect. And if you had the 4-inch thick material, you could then go to 2-inch thick, but I'm getting ahead of myself. So if you look here, we took 2 inches wide by 5.5 inches wide times 2 squares. That gets us our 22 square inches of material. Now it's surface area, not thickness. So make sure you don't get confused on the thickness of the material when you're calculating surface area for your static loading. So now let's kind of walk through an example and see how we can go about doing this. So let's say your current package uses a 4-inch thick polyethylene cushion. When you drop it from 30 inches, it has a peak deceleration of 30 Gs. The velocity change is 240 inches per second. Can we reduce the amount of packaging? Anybody out there? Any hands? Any comments?
Greg, we have a question. So I see that you're talking about foam cushioning. What if I want to use a non-standard cushioning material?
A non-standard cushioning material, you would want to go to the supplier of that cushioning material and see if they have cushion curves for that material. Westpac has done cushion curves for bubble wrap, for molded pulp end caps. You can build out a cushion curve for any cushioning material. And if the supplier doesn't have cushion curves, you can send them our way, and we'd be more than happy to partner with that cushioning manufacturer to build those cushion curves out. Because we want to try and help in any way we can to get to a more sustainable world, and building cushion curves is one of those ways for non-standard materials, right? Polyethylene foam's been around as long as I've been in the industry. And, if we can come up with cushion curves for non-standard or new novel cushioning materials, that will help the packaging engineer do their job much better. Great question, Roy. And I see we have a few hands up of, can we reduce the amount of packaging? Really, you don't know based on just this information, right? Of knowing that your peak Gs from your package drop is 30 Gs, right? You need the damage boundary information to be able to tell if you can reduce your packaging. So now let's go, you convince the team that we can do damage, you need to do damage boundary testing to see if you can reduce that cushioning material. So you conducted a damage boundary test and you found a critical acceleration of 80 Gs and 140 inches per second. So now we know we have 50 Gs of margin in our existing cushioning material. So now let's look at a similar cushion curve for a 30-inch drop. And if we had used the 4-inch thick material, if we looked here, looking at loading at the belly of the curve, we could drop all the way to 2-inch thick material and reduce our packaging material by 50% without changing any of the characteristics. That would also allow you to reduce the size of the package and reduce the amount of corrugated fiberboard material you're using. And, just kind of, you would be able to fit more in a container ship and all of those things, which would help reduce the amount of fuel being used to ship your product around the world. And it just expands from there. So, you can easily reduce that. And that was all done because we knew how much it took to break the product. Cool. Roy, back over to you.
Greg, thank you very much for that great information. I would also like to thank everyone who attended and submitted questions. We truly appreciate each of you. For anyone whose questions did not get answered, we will respond to you directly via email within a few days. If you missed anything or would like to listen to this webinar again, please go to our website, westpac.com, under the Resources Webinar tab. The webinar materials will be uploaded within the next couple of days. Thank you for attending today's presentation, and thank you, Greg, for a great session.
Thank you, Roy. Thank you, everybody. Have a great day.